So buffers. Usually when you have a solution and you add an acid or a base, the pH changes significantly. But a buffer, if it's present, will resist that pH change. And doesn't resisting a change make you think of Le Chatelier's principle? In equilibrium, you do something to it and it's like, nah, I don't like that, and it tries to undo it, right? Buffers are like that. A buffer needs to contain significant amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. A weak base or acid alone doesn't have enough of the conjugate to act as a buffer, so we need to put both of them in there. So formation of a buffer illustrated. So take a weak acid. Weak acids can neutralize bases. We put that into the solution. Here we're using acetic acid, a weak acid. We also add the conjugate base. The conjugate base can neutralize acids. So the conjugate base of acetic acid is acetate. So we'll mix sodium acetate with acetic acid. And now we get a solution where there's roughly equal amounts of the conjugate base and the weak acid. This does not happen in a solution of weak acid alone, because weak acids only dissociate a little tiny bit, like 10%, right? And so there's just not enough of the conjugate base to be effective. Okay, which of these solutions is a buffer? What are we looking for? Weak acid and conjugate base. So here we've got HNO2. Is that a weak acid? It's not one of the six. Yes, it is. Weak acid. Is this its conjugate base? No. No, that's a strong acid. That's messed up. HNO3 and NO3. Strong acid or weak acid? That's a strong acid. This is the conjugate base, but it's not going to do any good. Here we have HNO2. Okay, we've already established that's a weak acid. Is this the conjugate base? Nope. That's the conjugate base of a strong acid. That's not going to help. So it must be this one. So here we have the weak acid, HNO2, and its conjugate base. Yes, there's a sodium there. The sodium is just the partner for the conjugate base, because you can't have ions, just negative ions running around. There have to be positive ions. Okay, it's a buddy system, you could say. So any questions? So how do we calculate the pH of a buffer solution? So this is like a whole bunch of stuff from chapter 17, right? We just talked about pH of acids and bases. This is sort of a continuation. So let's look at a solution that starts out as 0.1 molar acetic acid, 0.1 molar sodium acetate. Weak acid is conjugate base. So the presence of the acetate ion causes the acetic acid to ionize even less than it normally would, and that results in a less acidic solution. So that's known as the common ion effect, and we'll see that in several places in this chapter. So here we're looking at the acid ionization of acetic acid. It reacts with water, it donates a hydrogen to the water to make hydronium ion, and produces acetate. There's a Ka, an equilibrium constant for this. If we put some acetate in here, though, that's going to cause this equilibrium to shift and have less acid dissolve. So the common ion effect is if you add an ion that's common to what's in the equilibrium, it's going to affect the equilibrium by Le Chatelier's principle. So calculate the pH of a buffer solution that is 0.2 molar in H2H3O2 and 0.1 molar in NaC2H3O2. And Ka for this acid is 1.8 times 10 to the minus 5. Well, we need to write a chemical equation. I'm going to use A, so this is HA, and this is Na plus with A minus. So we've got our acid, and it's going to release a hydrogen ion and produce the conjugate base. You can use that for any weak acid. Now what do you think we need? Ice table. So many ice tables. Because we have an equilibrium. And an ice table is how we can calculate concentrations in an equilibrium. So we're looking at our initial concentrations here. It's 0.2 molar of the acid, so 0.200. How much hydrogen ion is initially present? Approximately 0. How much acetate is initially present? 0.1. Now in chapter 17, we were just looking at the acid without anything else added. Now we're, stepping it up a little bit. So here we have 0.1 molar of the sodium acetate, so 0.100. So because of this hydrogen ion concentration is going to be lower than if it was just acetic acid. So now we look at changes. So this side has a 0, so it can only go up. So plus X, and the other side is minus X. So 0.200 minus X, and we have X, and 0.100 plus X. When I said we'd be doing a lot of these, I was not kidding. So we have Ka for this, which is the H plus times the A minus divided by HA. And that's 1.8 times 10 to the negative 5. And that equals X times 0.1 plus X divided by 0.2 minus X. So, some of you, please do the solver. I'm going to see if X is small is going to work. Oh, that looks pretty small. I'm going to divide that. When I check X is small here, I want to divide by the number that's going to give me the smallest percentage, so I'm going to divide by the biggest one. No, I'm going to divide by the smallest one. Yeah. Brain fart. Divide by 0.1 times 100. Yep, 0.036%. 0.04%. So X is small. What did you get with the solver? About the same thing? 3.59? 98 times 10 minus 5. Yeah, rounds to the same thing. You can use either method. Use the one that makes more sense to you, that seems easier for you. So what we found there is X. What is the hydrogen ion concentration? It's X, right? And so it is 3.6 times 10 to the minus 5 molar. And then for the pH, we take the negative log of that. Oh, I should at least do this. I paused it somewhere. I'm sorry, YouTube people. Try the video for the Tuesday, Thursday section, because hopefully it won't happen again tomorrow. Okay, so we can derive an equation that relates the pH of a buffer to the initial concentrations of the buffer components. Because in that example, we ended up being able to use the X is small approximation, and that just involved using Ka and the initial concentrations. Well, let's see if I can remember how to do this. So I'm making an ice table here. The initial concentration of the acid, this is 0, and this is the initial concentration of the conjugate base. And so the change, minus X, plus X, and plus X. At equilibrium, we have the initial concentration minus X, and X, and the initial concentration of this plus X. So the equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. I just did the same thing we did in the previous problem, except I don't have numbers. I have a variable for these concentrations. So this one ends up being minus X, that one is plus X, and we get this. If X is small, then those X's that are being added and subtracted are 0, essentially, right? And so then that simplifies, and it ends up being X times the concentration of A minus initial divided by the concentration of the initial acid. Did not leave myself enough room to finish this. How do we get pH? Negative log. So which of these letters in here are going to be the hydrogen ion concentration? X, right? X is the hydronium ion concentration at equilibrium. So to find the pH, we need to find the negative log of X. So let's do this. We'll see that name again later. So I'm going to take this equation down here. Oh, it doesn't work. Okay, never mind. And I'm going to rearrange it. So to get x by itself, I'm going to multiply both sides by HA and divide by A minus. So I get x is equal to KA times HA over A minus. Then I'm going to take the negative log of both sides. Oops. Let's make some more room. Negative log of x is pH, yes. Negative log of Ka is pKa. Now, we could keep this as negative log of HA over A, but we could also change the sign by inverting these guys. So we have plus log of A minus over HA. And this is called the Henderson-Hasselbalch equation. That's a mouthful. Why do we mess around with this? Well, I can think of two reasons. One, it's better to not have negative signs in there because they mess things up. But the other thing I like about this is when we look at the equation for a weak acid, A minus is the product and HA is the reactant. Because we have to remember which one of these goes on top and which one goes on the bottom. In this way, it follows the same pattern, products on top, reactants on the bottom. You do not need to know how to derive that equation. Hooray. We just need to know how to use it, okay? Any questions? So the Henderson-Hasselbalch equation, this works only if x is small, right? Because we had to get rid of the x's that were added and subtracted. And so when will this work? If our initial concentrations are not too small and K is fairly small. And we need the acid concentration and the base concentration to be greater than like 100 to 1,000 times larger than the Ka. You can always use the equilibrium approach and a solver and find the pH. That's always valid. Henderson-Hasselbalch equation works a lot of the time and is faster, but it doesn't always work. Okay, let's use the equilibrium approach and the Henderson-Hasselbalch equation, and we're going to find the pH of a buffer solution. So we've got 0.25 molar HCN, 0.17 molar KCN, and for that acid, the acid ionization constant 4.9 times 10 to the minus 10. You see this is nice and small. pKa is 9.31. Use both approaches to find the pH. How about let's use the Henderson-Hasselbalch equation first? Because we just learned how to do it. It's shiny and new, and it's fast. So Henderson-Hasselbalch equation says the pH is equal to the pKa plus the log of the base. So here the conjugate base is Cn minus, and the acid is HCN. So what we're going to do is we're going to plug in pKa, 9.31, plus the log of the base, 0.170, divided by the acid, 0.250. Okay? We solved a problem without an ice table. Any questions about that one? Let's use the equilibrium approach. So we've got HCN in equilibrium with H plus and CN minus, making our ice table. ICE. We have initial concentrations for HCN, 0.250, and for CN minus, 0.170, and the hydrogen is approximately 0. Then we do the changes. This one's 0, so this side has to be plus X. The other side has to be minus X. We were given Ka as 4.9 times 10 to the minus 10. So that's going to equal X times 0.170 plus X divided by 0.250 minus X. If we do the X's small approximation, we're going to end up with exactly the same thing. So let's do the solver on this one. So 4.9 times 10 to the minus 10 is equal to X times 0.17 plus X. And in the denominator, we have 0.25 minus X. Okay, this is fun. I got minus 26. Anybody else get that? Is that even possible? No, that's not even possible. So the first thing I'm going to do is I'm going to go back and check my equation. Yes, I messed up. Instead of the X button, I pressed X squared or something. And so I've got X raised to the power of, Okay, let's try that again. This is showing me 7.2059. That seems a little big, doesn't it? Scroll up to the X line, and it'll give you the rest of the number, times 10 to the minus And I actually have to scroll over there to get it. Minus 10. Well, that's inconvenient. Here's another way you can do it. Get out of the solver. So go quit. And then hit that variable button, X, and press equals. And it brings you the value of X. And we don't have to scroll around. So that's a potential pitfall when you're using the solver. If you just write down the first few digits of what it shows you, you might be missing something really, really important, like times 10 to the minus 10. So to find the pH then, we need the negative log of that. So the pH is 9.1423, 9.14. Same answer. Both methods work, provided that X is small. Because when X is small, this collapses, these go away, and this becomes a much simpler equation, and that's how we derived the Henderson-Hasselbalch equations. We just rearranged that and took the negative log of both sides. So most of the time for a buffer, Henderson-Hasselbalch equation works. Any questions? I also am not going to quiz you on spelling or pronunciation of Henderson-Hasselbalch. 9.14. Okay, so that's how we calculate the pH of a buffer solution. How do we calculate changes in the pH of a buffer solution? So a buffer resists change in pH, but the pH does change a little bit. So we have to break this down into two separate parts. We have to look at the stoichiometry, and then we have to look at the equilibrium. So in the stoichiometry calculation, we're going to find out, well, how much does that addition change the relative amounts of acid and base? And then with those numbers, we will do an equilibrium calculation. It's a conceptual question. A buffer contains the weak acid HA and its conjugate acid A minus. The weak acid has a pKa of 4.82, and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and conjugate base in the buffer? This problem should be before the previous slide. Well, we don't need to do any calculations here, but we do have to think about mathematical relationships. So here's the Henderson-Hasselbalch equation. The pKa is 4.82, and the pH is 4.25. So I guess we can think about it without that as well, but so this is what it would be as a pure acid, and this is what it is in the buffer. Do we have more acid or more base to make the pH go lower? There's more acid, which means there must be less base. So I'm going to choose this one. The conjugate base is lower in concentration than the acid. So that would be A minus being smaller than HA. So that means that this fraction is less than 1. So let's call it 0.9. What's the log of 0.9? If you're thinking cap isn't on, just do it on your calculator. It's a negative number. When this ratio is less than 1, that will bring the pH down. When it's greater than 1, it brings the pH up. I should have left Henderson-Hasselbalch out of that, but sorry. Okay. The stoichiometry calculation in finding the pH change in a buffer solution. So here's our example problem. We have 1 liter of buffer, and it's 0.1 molar in both the acid and the conjugate base, and we're supposed to calculate the pH after adding 0.025 moles of strong acid. So we're going to find out how that changes the initial, the concentrations or the relative amounts. Okay, so these tables are going to be slightly different than the tables in the textbook. Okay, they do a before, after, and change. You can do that. No, before, after, before addition and after. It's confusing. And I just don't like how it works. I've tried using that for years now, and it just never works very well. So I changed the slides, and we're going to make an MCM table. So we're looking at the moles initial and the moles after. So we're going to look at, well, how many moles do we have initially? And we have to look at molar amounts. Moles, not the molarity. We have to work in moles. So we have 1 liter of this concentration. So the math is really simple then. 1 liter times 0.1 molar is 0.1 moles, right? So I'm starting out with 0.1 moles of the acid and of the conjugate base, and I'm adding 0.025 moles of strong acid. Now, why did I write it this way instead of HA dissociating? Because we're thinking about stoichiometry. And we're adding this to what we already have. So we're adding this to that, and we're going to see what happens. This is a very simple limiting reactant problem. So we have a 1-to-1 stoichiometry. This one has a smaller number of moles. We're going to assume that it reacts completely. And so we're going to take the smaller one, and that one's going to be our change. So we're going to react all of this and end up with approximately 0. So that went down by 0.025. This one also goes down by 0.025, and this one goes up. So if you want the lines in there. So this side of the arrow is going up, this side of the arrow is going down. Any questions about that? This is new. We haven't done this one before. Not an ICE table. It's an MCM table. So adding the small amount of strong acid is equivalent to changing the initial concentrations. So we're going to take those numbers we got from the stoichiometry problem, these guys. Those were in moles. Here we can do this calculation in moles because the volumes are all the same, and so they will cancel out. You can also convert back to molarity and do it that way. So here's what we started with. 0.125, approximately 0, and 0.075. This is after looking at the stoichiometry from adding that acid. And then we've got minus x plus x, and we do all of that. So then we would finish this up with the Ka of this acid, which is not given to us, x times 0.075 plus x, divided by 0.125 minus x. So when we add acid or base to a buffer, we add an extra step in the calculation. We have to look at the stoichiometry first before we make the ice table. Any questions? What if we're adding base to the buffer? Well, it's exactly the opposite. So if we're adding 0.025 moles of base to that same buffer, then in our MCM table, the moles initial, that's what we're adding. This is what was here from the buffer. And then again, we're going to look at a limiting reactant problem. And we're going to have one of these get all used up. So this one, we're going to use up all of that. So this one ends up being essentially 0. And we're going to subtract that over here and add it over there. And this approximately 0 is, kind of back to what the quote was, right? You can't actually have 0 concentration. So, summary, if you add a small amount of strong acid to the buffer, it's going to convert a stoichiometric amount of the base to the conjugate acid. It's going to make more acid, and that will cause the pH to decrease. That makes sense. If I add acid, the pH is going to go down. Because it's a buffer, it's only going to go down a little bit instead of a whole lot. If I add strong base to the buffer, it's going to convert acid to base, and it will increase the pH. So here is an interesting figure. So in the middle here, we have our initial buffer. We have equal concentrations of HA and A minus. And they're represented as a bar graph here and also in pictures. If I add H plus to this, the A minus is going to react with the H plus and make more HA. So my HA increases and my A decreases. Where did those extra 2 come from? It's these guys. These guys, hydrogens came in to react with these guys, and so then they move over to the other column. If I add hydroxide to this, it's going to pull hydrogens off, and so we're going to get more of the conjugate base and less of the conjugate acid. It can take a while to get the idea of what a buffer is doing. Once you see it, it's beautiful and it's actually simple. But before that, it kind of seems to go in circles. In the buffer, you have acid and base. If you add acid to it, the base reacts with it. If you add base to it, the acid reacts with it. It can do either. It's like Superman. Neutralize anything. Questions? So this is that figure we just looked at. So which image best represents the amount of hydroxide that was added to the buffer in part B? So here, when we're adding hydroxide, did we add 1, 2, or 3 molecules? I heard little mumblings. Well, how many of these moved to the other side? 1, 2, 3, 4. 1, 2, 3. One of them did, right? So one of these was reacted with. So that tells us that we added 1 OH. Does that make sense? In a 1 liter buffer solution, 0.1 molar acetic acid, 0.1 molar sodium acetate. Because the initial concentrations are equal, the pH is equal to pKa, which is 4.74. Calculate the new pH after adding 0.015 moles of sodium hydroxide. stoichiometry, and then equilibrium. So I'm adding hydroxide. It's going to react with the acid. Bases and acids neutralize each other, produce water and the conjugate base. And so I guess we could call that MICMA. Moles initial, moles after. So initial moles, we're adding 0.015 moles of sodium hydroxide. And how many moles of HA did we have? 0.1. So here they're being nice to us. They're actually telling us what the moles are, instead of just giving a molarity and a random volume. And 0.1 mole of the conjugate base. And water doesn't change. So we're going to react these completely. That's why I drew a single arrow here. The OH minus is a smaller number, so that's the one that's going to get used up. So I'm going to subtract 0.015 from that and get approximately 0. I'm going to subtract 0.015 from this, and I don't trust my head today, 0.085. And then over here, we're going to add. Everybody okay with that? These are the amounts that I'm going to use in my ice table. So now I'm going to look at the acid of my buffer and how it ionizes. And my initial concentration of acid it's 0.085 moles in 1 liter. They say you can do it in moles. I think it's better to just always do it in molarity. 0.085 divided by 1, so this is 0.085 molar. And the A minus is 0.0115. And hydrogen ion is essentially 0. So then I've got minus x plus x plus x. We could also most likely use the Anderson-Hasselbalch equation. So the A minus is 0.115, and the HA is 0.085. Okay, what does X end up being if you use the solver? Did anybody do that? 1.33 times 10 to the minus 3?
Or to the
Negative 5? Okay. So the negative log of that would be the pH. Which equals 4.8761. 4.88. Slightly different, but not enough to matter. The 1.33 times 10 to the minus 5, we divide that by the smallest one, which is the 0.085. That's 0.02%. So the X's small approximation does work there, and we can use Henderson-Hasselbalch. Most of the time you can use the equation. Sometimes our students call it the HH equation. Any questions? We can also have a buffer made out of a weak base and its conjugate acid, like NH3 and NH4Cl. So the calculations here are going to be very similar to a buffer of an acid and its conjugate base. If we're going to use the Henderson-Hasselbalch equation, we have to calculate Ka for the conjugate acid of the weak base. And that's really not too hard. pKa plus pKb equals 14. So here we're using a weak base like ammonia. We're putting that in there. We're also adding the conjugate base, which is ammonium. And now we have lots of acid and conjugate base. It can neutralize whatever acid or base we throw in there. We're going to use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution composed of a weak base and its conjugate acid. So here we've got a 1 liter buffer, 0.5 molar ammonia, 0.2 molar ammonium chloride, and we've got 0.01 moles of solid sodium hydroxide being added. So we still need to do the stoichiometry. So we're adding hydroxide, and the hydroxide is going to react with the NH3 or the NH4+. It's going to react with the NH3. This is the base. Sorry. No, you're right. I'm wrong. Don't listen to me. What do I know? Yes, NH4+. The base reacts with the acid. Just shoot me now. Sorry about that. And it's going to make water and ammonia. Moles initial, change, moles after. So we're adding, bless you, 0.010 moles of OH. How many moles of NH4 plus do we have? We have 0.20. It's 1 liter of this. And we don't care about that water. And we've got, it's 0.5 molar in ammonia. So 1 liter times 0.5 is 0.5 moles of that. We're going to take the smallest one here and subtract it on the left and add it on the right. Henderson-Hasselbalch is the pH is equal to the pKa plus the log of the conjugate base over the acid. It might make more sense if you say concentration of base divided by the concentration of acid. Because you look at this and you're like, I have no A, what is HA and A minus here? That's confusing. It's base and acid. The Henderson-Hasselbalch equation has pKa in it. It does not have pKb. Could you derive a Henderson-Hasselbalch equation with pKb in it? You could, but nobody does, because we don't really need to. To get the pKa, all we have to do is take 14 and subtract 14, 4.75. So we find the pKa, it's 14 minus 4.75, which would be what, 9.25? Yeah. So pKa, bless you, is 9.25 plus the log of the base concentration, that's this guy right here, 0.51, divided by the acid, .6788. Any questions? Did I get the answer right? On the slides, you've got the answer up in the corner. 9.68, I did. Questions?